Hi everyone, this is Thiagarajan, retired Deputy Chief Engineer from Indian Railways. So in this video, I am going to discuss something about the layout designs for railway station, okay, in Indian Railways. So here, specifically, I am going to discuss about the different type of connections and with a numerical example. So how they are designed, okay, how we are getting the required data. With the data, how we will be able to fix the geometry on the ground that you are going to see. It is a part 2. So earlier part 1 video also I have just uploaded that I have given some introduction about the layout designs. Okay. So when the layout designs are not properly done and what will be the consequences, and it's little trigonometry also I've touched, which are required for doing the designs. Okay. So we will go to the subject. So as already discussed, this is a view of a station yard. You can see how many lines are there, the different type of connections we have. Here simply some connection will be there. Here like some crossover arrangements. Okay, some symmetrical split arrangements like that. Okay, so those connections how we are going to do that we are going to see here. Okay. So even the previous video I have touched upon different type of connections we have. Once again, just I want to recollect. This is this is a divergent track connections. Okay, of siding coming and connecting with the main line. How it is to be done? We have different types. The angle of inclination of the divergent track or the siding tracks makes with the main ends equal to the angle of crossing. Same angle of crossing how it is to be done. Okay, and coming to next, when the angle of crossing is less than the angle of inclination. Okay, how it is to be done? Here the angle of inclination is less than the angle of crossing. How it is to be done? Here something about the connections between the two parallel lines. The normal distance with large distance and still larger and crossover, simply crossover with the normal distance. Crossover means introducing 2 points on crossing on 2 lines, giving the connection. Okay, ensuring the movement, through movement as well as the turnout movement on both lines. Okay, like that. The same crossover with some large distance between the 2 lines and still larger. Okay, how can be done? Introducing a reverse curve with the straight. Here parallel lines with a different angle of crossing. With this we can connect it. And another method of connection we have symmetrical split. Normally snag and we used to provide symmetrical split on one end for isolation purpose. In this case see how it's to be connected. Here 1 in 12 may be there. Here normally only 8.5 symmetrical split. So it is to be connected. Okay, these arrangements. And another arrangements, sometime always we can't say the lines will be parallel. There will be non-parallel lines also will be there. So that is the case how the crossover can be introduced. Okay, with a different angle of crossing or same angle of crossing. So these are all different type of connections we are going to see. And also we'll see slightly about that curved lines also. Okay, connection between the curved lines and crossover between the curved lines also. Okay, this is something about different type of connections. We'll see one by one each type of connections. Okay, so before that already I want just explained about this central representation of turnout in the previous video. To recollect, this is our points on crossing, but central representation is the red line is central representation. That means central line of the main line and turnout line. The intersecting is point is called point of intersections. The distance between them, SRJ, and the point of intersection we take as A, and from point of intersection to the heel of crossing we take it as a B. Okay, and similarly the other side also will be there. This point of intersection to heel of crossing also B. This equal to this, and of course this B is divided into M and K. That means point of intersection to nose of crossing, that is M, from nose of crossing to heel of crossing K. This is normally coming to use in case of curved lines. Okay, normal designs and all straight track connections and all, mainly we want this A distance and B distance, which is important. So simply if you take the central representation of the points on crossing, this will be like this. Okay, this is A, B on both sides. mainline side and turnout side. It's a point of intersection. This is inclination angle normally, according to your crossing angle, F. So for each points on crossing, we have the standard dimensions available, readily available. We can make use of these dimensions. Okay, for 60 kg, 1 in 8.5. Okay, and 50 kg. This is A value. This is B value. B value we take only modified only we take. Okay, earlier we were using B. Now some additional length we are adding the B, because after heel up crossing we want to keep some distance straight where we are providing common slipper. That is why for different angle of crossing some length is added. Okay, that already we have discussed. Okay, and coming to 12 in 12, this is your A value, this is your B value, and case of 1 in 16, this is your A 20.97, 13.558. This is B value, and similarly for 1 in 12 also. These are the dimensions available. You can make use of straight away. Okay, for easy calculation. Okay, and also I want to recollect something about sine rule, cos rule, tan rule, and tangent length. These are all things, they are all very much useful for designing our layout. Okay, so as far as pretty well already discussed also. As far as sine rules are concerned, it is in case of right angle triangle. This is the theta. So this will relate hypotenuse and opposite side. Suppose in our case, if you want to know y coordinate, this y axis, this x axis. Suppose y coordinate you want to know, we will use that the sine rule. Similarly, in case of this x, we want to find out the x coordinate. So we will use a cos rule. That is relating your hypotenuse and adjacent side. Okay, and of course the tan rule. So this is relating your opposite side by adjacent side. That means that is tan theta equal to opposite side by adjacent side, and cot theta is equal to 1 by tan theta. So this is also a very important equation, so you should keep in mind. Then coming to tangent length, of course, so already in detail we have discussed about the curve parameters, and particularly you must know this formula, that is tangent length equal to r tan delta by 2. So delta is equal to deflection angle. So tangent length equal to r tan delta by 2. Okay, so these things and all so will be requiring during the design of layout. Okay, now we'll see the design of different type of connections one by one. Okay, so this is a divergent track. Suppose a side line is there, and the extension it is intersecting the main line at an angle equal to theta. Okay, this is inclination angle. Suppose the angle of inclination equal to angle of crossing. This will be the connections, side connection only. Because for example, it is 1 in 12 crossing, you are introducing the main line. Okay, the angle of crossing for 1 in 12, 4 degree, 40, 49. Suppose here also same inclination is there, 4 degree, 40, 49. In this case, there is no need of provide any kinetic curve. So straight away, the extension it will interest somewhere in point of intersection. Here some point. Straight away we can introduce a point, we can connect it. That means the extension that will intersect the main line. It's called point of intersection. From here we can keep a distance equal to A. Okay, pretty well. This is for points on crossing, center line. Okay, representation. Okay, so in this case for point of intersection, when you are keeping a distance of A, that will locate your SRJ. So assembling a points on crossing, inserting here this location in such a way the SRJ should be exactly comes here. In this case, here if you are taking the side line further, you can directly connect. There won't be any kink. There is no need of any kinetic curve. This is the way you can do it, provided this angle of inclination and the angle of crossing is equal. Okay, this is the first type of connection as far as divergent track is concerned. Okay, the next one is suppose the side line is coming here and the extension it is intersecting with the main line. It's making an angle equal to theta. But theta is here, it is more than the angle of crossing. Suppose here we are using 1 in 12 points on crossing. Suppose here 40, 40, 40, 49. But whereas the angle of inclination, the theta equal to 6 degree or 8 degree. In this case, it is more than this. In this case, we cannot directly connect it. Directly, we cannot connect it with the heel of crossing. So, because of the change of angle, difference in angle, definitely there will be a change in direction. So, necessarily we have to introduce a connecting curve in between them. So, for this type of situation, you have to locate the SRJ, and also you have to locate the point up to which, you have to draw the striding line, and after that you have to start providing curve. So how to do that? Okay. So for that, we have to find out the distance, x distance and the y distance. Okay. So we have to find out. So so once we know the y distance and the x distance means x plus a, adding that we will get the overall length. Okay. So knowing this, the horizontal distance and vertical distance, we will be able to fix the SRJ. Okay. So drawing siding here, and we can fix the vertical offset here, the y. Then from here we can measure the distance equal to overall length. Okay. So once we are able to locate the SRJ, we can insert the points on crossing here, and we can give the connecting curve. Okay. But the x distance, it is only point of intersection. It is imaginary point. So this we cannot fix it. So x plus a, adding this, we will be able to get the overall length. So that will locate our SRJ. Okay. So we'll see in detail how. So we have to calculate these distances. Okay. So we have to simply using the trigonometry we are going to calculate here. So already we have discussed something, some sine rule and cos rule, and tangent length, formula we have r tan delta by 2 we have used, we have discussed. So using those formulas we are going to do it here. Okay. Then for fixing, first we have to calculate the x distance. How to calculate x distance means what? That means cos rule, using cos, and so we will be able to find out this distance. Okay. As far as y is concerned, it is sine. Using sine rule, we are going to do it. But here you see, so actually we want to get the overall length from SRJ to this point, that one tangent point. That's not distance. And vertical distance means y distance means the tangent point to the line, main line. Okay. Perpendicular, the offset we have to find out. So here you see, further we can divide into triangles conveniently. Okay. This is first triangle, this is second triangle. The first triangle we are able to get the adjacent side. So we can get the distance up to this point. And again taking this triangle, we are able to get the adjacent triangle. Okay. Distance. So total distance will be your x. So like that, using sine rule, this opposite side height and here this triangle height. So adding will get the y. So further what we do, as far as this triangle is concerned, once we know the hypotenuse, okay, we know the angle, so we can find out this distance. The hypotenuse means what? The b already we know. We have standard, when we are using 1 in 12 turnout, we know the b value. The standard dimensions available here. Then t we have to find out here. So we are going to fix the radius. Okay. Suppose normally when we have the 1 in 12 points on crossing introducing, normally the same curvature we can prefer. Okay. Same 1 in 12 lead curve radius we can fit here. Okay. So once we know the radius, radius we fixed, we will be able to get the tangent length. How to get tangent length? We have the formula, the t equal to r tan the deflection angle divided by 2. Here deflection angle, what is deflection angle here? So we have to find out here. Here we know the crossing angle f. This is an angle theta, that means the siding track, making the angle with the main line, that's equal to theta. So we know the theta and f. Suppose if you take this triangle, see, suppose this triangle, so this angle we want to, this is your deflection angle, this angle, this is your deflection angle, this angle is equal to deflection angle, this angle equal to deflection angle. So you know operative already we have seen this triangle, the exterior angle equal to the sum of opposite internal angles. That's the rule. Okay, that means you know this plus this equal to this. So this we want to get this minus this. That means theta minus f will be this deflection angle. So once we know deflection angle and r, we can get the tangent length. That's what here formula. First we are finding on tangent length. T equal to r tan theta minus f divided by 2. So we got the tangent. Then we have to find out the horizontal distance of this triangle. That means Pn, point of intersection to the end point. That's equal to what? B plus T. That B plus A hypotenuse into cos f, the cos rule, cos f. We will get the distance up to this point. Then again, if you want to get this distance, you know, you are taking this triangle. Here we know tangent length. So T cos theta. Here this is theta. This angle theta means this angle equal to theta. This angle to theta. So T cos theta. So this m1 plus nm will be your x distance. That's what here. X equal to b plus t cos f plus t cos theta. So this is x distance. Like that, overall length we can find out. So overall length means you know x distance we have calculated. Adding the value of a, we will get the overall length. Okay, like that vertical offset, you know, it's that means this offset y distance. It is a sine rule. Okay, same thing, same this thing, only we are putting in place of cos sine. So b plus t sine of this one, then t sine of this distance. So total distance equal to y equal to b plus t sine of plus t sine theta. So we are getting it. Once we know the overall length and y distance, from this point we can measure the distance, okay, perpendicular to the main line. Fixing the point m, from here we can measure the length equal to overall length. That will locate your SRJ. So after locating the SRJ, we can insert the points on crossing exactly here, and if you are connecting with the radius we have chosen, we will be able to get the perfect connection. So okay, this is what so we have to do as far as divergent track is concerned, in case the inclination angle is more than the angle of crossing. Okay? This is the procedure. So some example also they given here. A broad gauge siding is required to be connected to a mainline track using 50 gauge 1:12 turnout. The angle of intersection between the two tracks being 10 degree. It is more than the 1:12 crossing. That 1:12 crossing 4 degree 45 49, whereas the inclination angle is 10 degree. So calculate the required distances for the layout, assuming the connecting curve starts from the heel of crossing. So we are connecting curve starts from the heel of crossing. So the given is the angle of crossing and the A distance, B distance they given, and radius of the connecting curve here. Okay. Here one thing I want to say here. See, actually our 1:12 turnout radius is lead curve is this one R. Suppose you want to adopt the same radius of lead curve, as a connecting curve radius. In this case, we have to take the R dash, that is equal to R minus J by 2, because this radius is equal to this outer rail radius. But whereas, as far as our case concerned, we are doing everything Sutherland method. When you are doing it, that R will be equal to Sutherland of the curve will be equal to R minus J by 2. Suppose actually this is one road layout they are given. Road layout means other than PS repairs, the radius minus J by 2 they are given. As well as presently for PS repairs it is 441 360 I think, minus J by 2 1676 divided by 2. We will get something. So that radius you can fit. If you want to adopt the same radius, okay. So that thing I want to clear it, okay. Then of course here now we can just find one by one. That is first, for finding out our overall length, you want to find out the x distance, and for the, first we must know the t, tangent length. So tangent length, the formula already discussed, r tan theta minus f divided by 2. Substituting here this radius and all the angles, 10 degree inclination angle minus crossing angle. So you are getting the tangent length equal to 20.179 meter. Then x distance, of course, it is a cos adapting, horizontal distance. The p plus t cos of plus t cos theta. Substituting here everything, we got 63.879 meter. Like that, overall length, the x plus a distance. So point of intersection to the tangent point, where the curvature starts in the siding, that point. So that x distance plus a. So we will get the overall length. Then y distance, this y distance from the main line to the siding track, where that line should come straight, So that point, the tangent point, the y distance equal to, in the same formula we are replacing cos of with the sin of, like that here, sin theta. So using this relation, substituting all values, so we are getting the y equal to 7.171. Once we know the y distance and the overall length, so we can fix the SRJ. So after fixing the SRJ, we can assemble the points on crossing there, and we can introduce the connecting curve between the heel of crossing and the tangent point of the siding line. So that we will get the perfect connection. This is a way we have to calculate the required data. With the help of these data, we are able to fix the geometry on the line as far as this case is concerned. That is, divergent track with the angle of crossing is less than the angle of divergent track. Okay. So we will go to the next type. Okay. So this is also divergent track connection. Here, this the angle of siding, the inclination angle is lesser than the angle of crossing. When this is the situation, how the connection has to be made. It is similar to the previous case. The earlier case, this connecting curve was in a same direction of fluxing. Okay, it will continue here, the turnout, then the crossing portion straight to be there. Again, we will have the connecting curve. But here, because of the angle of inclination is lesser than the angle of crossing, here that there will be a reverse curve. Okay, only the difference is there. So all other things are same only. So for the fixing the the coordinates, point of the SRJ and the point of tangent, So we need to know the distance, y distance and the x distance. Then once we know the x distance, x plus ca, will get the overall length. So from here we can measure the y and we can measure the overall length. We can fix the SRJ. Then after locating this one is inserting the point here, and we are able to give the perfect connection here of the desired radius. Okay, whatever desired radius you have proposed, for the radius we can give the curvature here. Okay, so how it can be done, we'll see in detail. Okay, so this is a detailed drawing of this connection here. Divergent track, it's making main line an angle equal to theta. So, but we are fitting in a crossing, the angle f, that is more than the angle of inclination angle. When this is the case, this will be the shape of the drawing here. Similar to the first case, second case. So here also we have the two triangles here. Two triangles we conveniently, dividing, and each triangle, if you are able to find out the adjacent side, will be able to get the value of x, and the opposite, if we know the both triangles, we will be able to fix the y distance. Simply the same formula. Okay, but only thing we have to find out the here hypotenuse length. So first triangle b plus t hypotenuse, and second triangle T is your hypotenuse. T means tangent length. So here B is, of course, we know for the, suppose when you use 1 in 10 points and crossing 1 in 12 dimensions and all, we know the measurement is, it's available, readily available. So we can make use of that. Only thing here, we have to find out the tangent length. So for finding out tangent length, what we have to, we must know that we know the formula, no? T equal to R tan deflection angle divided by 2. So R we can fix the same radius of turnout, we can fix here, or as per the manual provision, we are supposed to provide the minimum radius, based on site condition, we can decide. Or whatever BG, it was 350 meter radius, minimum radius, or 220, that too in case of any space constraint and all. So we can go, provided this mean, the condition of track should be at par to the main line, like that. There are instructions, we can follow that. Okay, here let us assume that we will have the same radius of turnout. Okay, but you have to find out the deflection angle. So R we fixed, and we must know the deflection angle. Then only you can find out the tangent length. So here, suppose if we take this triangle, this is our deflection angle. This angle we want to know. If you take this triangle, the sum of internal angles, opposite angles will be equal to your exterior angle. So x is equal to F. So that means this plus this equal to F. That this angle will be equal to this minus this. Okay, this minus this. So F minus theta will be your here deflection angle. So fitting here, we can find out the tangent. So T here, T equal to R tan F minus theta divided by 2. Of course, X the same way in the previous case, we have to do it. X equal to B plus T cos F plus T cos theta. Then overall length, of course, X plus A. And the Y distance, this is sine rule here, because vertical, opposite side, relating your hypotenuse. Here B plus T sine F will be your this portion, and T sine theta will be this portion. So we are getting the Y. So this is a way using these formulae, and we will be able to find out the Y distance and the overall length, and reference to this point, fixing Y overall length, we will be able to fix the SRG. So again, insert the points and crossing, and then we can give the curvature. Curvature, being a small curve, we can follow, the small setting of the curve. We already I have uploaded one video for setting of the curve, that you can also go through that. Simple way of setting of the curve and all is there, that by offset from chord or successive bisection of arcs, using those methods we can set out the curve. Okay, this is the way. So this is example. So the same thing, suppose here a broad gauge siding is required to be connected to a mainline track using 50 gauge. Here only end of turnout. The angle of intersection between the two tracks is 3 degree here. Calculate required distance for the layout. Here F is 6 degree 42 35. For only 8.5, crossing angle is 6 degree 42 35. Whereas the angle of inclination of the siding is 3 degree. So it is lesser than your angle of crossing. That is why this method, second, what we have seen on that method we have to plot. There will be reverse curve of the connecting will be the reverse curve with reference to turnout. Then A of course we know, then B of course we know for the 1 in 12, 1 in 8.5 cross, points of cross. Or here 220 or 522 we have taken, because same radius of 1 in 8.5 they have taken. And here also, suppose the same means this radius of lead curve minus G by 2 will be your center line of the radius that they have taken actually. Okay, using this this available data, then you have to go for design, and first you have to find out the T using the formula R tan F minus theta divided by 2, and we got 7.114. Similarly, X distance we can find out, substituting all the data available given, then we can find out the X distance 33.969, and overall length equal to, of course, the X plus A also they given, that point of intersection to the SRG. Adding that we will get the overall length. Then y distance, same formula, vertical distance, opposite side, b plus t sine f plus t sine theta. So we got 3.528. So we got now 3.52 y. Once we know the y distance, okay, we will be able to fix the tangent point as well as the SRJ. Okay, so we can keep the distance y, okay, perpendicular distance, and marking the point on the main line, and from here we can measure the distance equal to overall length. So that will locate your SRJ. Once you know the SRJ, you can assemble the points on crossing, insert in position here. Okay. Then after that, you can introduce a connecting curve. So connecting the heel of crossing and the tangent point, you can connect the curve. So this will be in a reverse curve form. Okay. Being a small curve, now you can use some offset method or successive bisection of arcs method. Okay. Or any latest, we have off late, total stations. Using that, we'll be able to fix the curvature. Okay. So this is about the the design of this divergent rock when the siding track intersecting with the main line. The angle of inclination is lesser than the angle of cross. Okay. This is something about it. Okay. Next, we'll see the connection to the straight parallel tracks with a normal distance. Okay. So normal distance means what? Normally, in the passenger, the station yard, station yard, we used to have so many lines, main line, loop line, and all. There and all, we used to keep the minimum distance. We will not keep more distance and all. Okay. So as per schedule dimensions, we have minimum distance, some 5.3 or 6 meters, something like that. You can have it. Okay. If that is the case, how to do the connection between the loop line and the main line to do the connection. Okay. Suppose, for example, when we have the one-integral crossing means, then normally we used to prefer one-integral curvature. Okay. Or otherwise, the curvature, it has been prescribed in Indian development manual. The minimum radius we are supposed to ensure it. Okay. If we have the perfect even flatter radius, we can start the curvature from the heel of crossing. Or if you want to give the minimum radius, putting the minimum radius here, and we can introduce some side portions. This is also okay. Okay. So how to do that here? So already as discussed, we have the formula and all, and trigonometrically we can resolve this. For fixing that, what we have to do, we have to find out the tangent point and as well as the SRJ locations. And for that, we need to know the overall length we have to find out. Okay, overall length we have to find out. So for overall length, first we have to find out the x distance, and adding with the a, we'll be able to get the overall length. Okay. How to get the x distance is the horizontal distance. It's okay. You can take this triangle. Okay. This, when we are solving this triangle or horizontal distance, we will come up to this point, and from that we are adding the tangent length. So we will be able to get the total length of x. Okay, and further we want to find out the tangent length first, t. Once we know the radius of a curve, what we are going to fix, with that, using the relation or tan delta by 2, deflection angle divided by 2, we can find tangent length. Here deflection angle equal to how much? Here deflection angle is equal to f, because here angle of crossing is f. This is a parallel line. Okay, this corresponding angle, this angle equal to this angle. Okay. So automatically this deflection angle equal to f. So from here, using on this formula, t equal to more tan f by 2, you can find out the tangent length. And next, now for finding the distance x, okay, we can take this triangle. Now since the opposite side is no, so we can relate this formula. We can take a tan rule, opposite side by adjacent side, that okay, that rule we can take. Here, as already discussed, in the crossover, like this earlier first example, I given. So this distance is equal to d cot of, d into cot of. That means d by x equal to tan f. So we want to know your the horizontal distance. Okay, this d into 1 by tan f. So 1 by tan f equal to cot f. That's why d cot of we take. So up to this point we come here, and after that we are adding the t, we will be able to get the total distance of x. So x equal to d cot of plus t. Okay. then overall length is equal to x plus a. Then if you want to find out the straight portion, suppose you want to introduce some straight portion in between, keeping the radius equal to 1 into some known radius. Suppose you want to keep some straight between the heel of crossing and that first tangent point, some sort of straight portion you want to introduce. You want to know the s. We can relate the formula, relating hypotenuse and the opposite side. So in this case, sine rule. So b plus s plus t, total hypotenuse, into sine of equal to our d distance. From this, we can rearrange and we will be able to get s equal to d by sine of minus b plus t. So this is a formula we can use for this one, overall distance over as well as the straight distance what is to be introduced, and also tangent length how much. Okay. So if you want to discuss in detail the same thing only, so this is the formula we have. Okay. And you can go to an example also. Here the BG main end track is required to be connected to a loop line which is parallel at 4.72 meter distance by using 20 kg 1/8 PSC CMS crossings, and calculate the required distances for the layout, assuming the connecting curve radius as that of the turnout curve radius. Okay. Here 1/8 points on crossing used, that is why f is equal to 6 degree 40-35. Distance they give 4.75, r is 221.522. That means radius of lead curve minus g by 2 they have taken here. And a distance, this is standard dimensions for 1/8 PSC CMS crossing turnout 12.02 meter, and b equal to 19.76 meter. This we can take from table. Okay. So once all values are we have, then using the formula you can find out. First we have to find out the tangent length. Then after that, using the relation all time f by 2, we got 12.991 meter. Then x distance we can find out. That means x equal to d cot of plus t, that 4.75 into cot of this one, or plus 12.991, that is t. Or otherwise d cot of, we can simply take the number. Cot of is equal to number. So d into 8.5, if you are multiplying, we will be able to get this value. This also we can take. Adding our tangent length, we will get the x distance, that is equal to 53.13 meter. So once we got the x distance, we can find out the overall length. That means adding a with the x will get the overall length. So we got okay, overall length is equal to 65.162 meter. Okay. Then s distance we want to know, that also using this relation we can find out. We got 7.63 meter. Okay, s distance. So once we know that, what we will do? So either if the SRJ is already known, fixing the inserting the points here. From here we can measure the distance equal to overall length. Okay, and marking perpendicularly, okay, in the loop line, that will locate your tangent point 2. Okay. Then once we know the tangent point, if you want to fix the tangent point 2, we can b distance, and yes also we have to extend the line. Okay, then angle equal to f further for a distance equal to s, so that we can able to locate the tangent point 1 here. So once we know the tangent point 1, tangent point 2, in between we can introduce the connecting curve, and setting the curve, being a small curve, we can adopt the simple method of setting out a curve. Okay, or you can use totalization. So once you are connecting this curve, one will be able to perfect connection will be able to get. Okay, smooth connection will be able to achieve. So suppose this point is known, from here we can come in reverse, locating the SRJ point. Okay, this is a way we have to calculate our required distances and we have to execute the work in the field, okay, for fixing the geometry on the ground. Okay, this is something about this connection to two parallel lines when a distance is normal. That means some 4.72 here, some 5 meters, 6 meters, something like that. So next is type is a connection to side parallax. Same connection, but the large distance is more. Suppose the distance is more, instead of 5-6 meter, when you have some 20 meter like that, how it is to be connected. In this case, if as already discussed, if you are having the straight connection, the overall length will be more, so that the clear standing room of the loop line will be affected by. At the same time, the overall length, since it will occupy more space. So in this case, what we do, we can introduce some reverse curve. The curve radius, the permissible radius we can provide here. In this case, how to do it? Okay, let's see this connection in detail here. See, so here we form a reverse curve in between the two parallel tracks and giving the connection with 1 points of crossing here. And first we have to decide the radius. So normally the radius we will keep at par to the, equal to the radius of the turnout what we are using. Since it is in the case of one passenger route line, normally we will have the only turnout only we use. Same radius will adopt here also. The radius we know. But for doing this connection, we need this dimension, that's overall length. So we have to find out the x, then adding a will get the overall length. So horizontal distance we have to find out. So as already discussed, already we have done, you can make some triangles and so that we are finding out the all horizontal distances, will be able to get the distance between the point of intersection at the tangent point here, where the curve is, ending. So further, first we must know the tangent. This tangent and another tangent. This tangent we are denoting as T, and for this curve we are denoting as T1. So finding out the tangent length, we must know the deflection angle. This deflection angle, as far as T is concerned, this is the deflection angle we must know. As far as this tangent is concerned, we must know this deflection angle. And further, we are conveniently making some triangles from there, so we are able to get some, the required the parameters, that is deflection angle. So here, what we do, we make the triangle O1 NO. That means this is your common tangent, this is your common tangent point, this is your radius of this curve and radius of this curve. This will be in a straight line because of this is going through the common tangent and common tangent point. Okay. So in this triangle O1 NO, let us take this is theta. So this cos theta equal to, cos theta equal to O1 N, then O1 O. That means in this triangle, this theta, pretty well the cos theta equal to adjacent side, hypotenuse, relating hypotenuse and adjacent side. Okay. This case concern, this is your adjacent side, this is your hypotenuse. Okay. So that again, that O1 N, how you can break to O1 L and L. And as far as hypotenuse is concerned, R plus R, 2R. Okay. So we take this triangle now. Because of finding out O1 L, we take this triangle. Here you can see this is your crossing angle and this is your the ordinate angle. This is also F. Then once this is f, total, this is your tangent radius, and tangentially it is connected, so that this angle will be equal to 90 degree. So this angle, this angle of this included angle of this triangle equal to 90 minus f. What this is 90 minus f, where this sum of triangle is 180. So here it is 90 perpendicular. So automatically we will get this angle equal to f. This is 90 minus f. So 180 minus 90 minus 90 minus f, we will get the f. So this angle is equal to f. So when this, we know this angle, okay, when we know this is r, then automatically that O1L equal to r cos f. Okay, and similarly, if you take LM, so let us take here, this is LM, let us take this triangle, this is f, so automatically this will be b sin f. This will be b sin f. That means this is b sin f will be your LM. So O1L equal to r cos f and LM equal to b sin f. And coming here, Mn equal to r minus d. That means, see here, come here, this total r minus d will be your Mn. Okay, that's what here. So with this, we can now fit in the cos theta formula, then we'll try to find out the theta. So here cos theta equal to what? So already O1L plus Lm plus Mn divided by 2r. We are substituting here r cos f plus b sin f plus r minus d divided by 2r. So from here we can find out cos theta this much, theta is equal to cos inverse of this thing. So we got the theta now. Okay. Once we know the theta, so we can get this angle. This angle equal to theta minus f. Okay, this is theta minus f. Because this theta minus f is the angle subtended center of this curve. Okay. So once we know the angle subtended center, that is theta minus f, that will be your deflection angle. Okay. Deflection angle of this curve is theta minus f. Okay. So we can find out the using a formula for tangent. This tangent is equal to r tan, here deflection angle divided by 2, here deflection angle equal to theta minus f divided by 2. So t r tan theta minus f divided by 2 will be your tangent line. As far as this tangent is concerned, t1, okay, this is theta. How? When this is theta minus f, this is f, automatically this is theta. Already we have discussed, that exterior angle equal to sum of opposite internal angles. This angle plus this angle equal to this. So this angle equal to how much? Theta minus f plus f will be your, this angle is theta. So once this is theta, automatically this will be your theta, deflection angle. So knowing this deflection angle, we can find out the T1. T1 equal to r tan theta by 2. That's what here. So now we are able to get the formula for T here and as well as the T1 also. Okay. Then another formula also we are forming, that is x distance, for x distance. So x distance what? Again, we are dividing conveniently triangles, making triangles for getting the horizontal distance. So let us take this triangle b plus t into cos f. Up to this we got. Then coming here, okay, you can come this triangle, you can make this triangle. So here t, this t1 hypotenuse. So t plus t1 into cos theta, this theta is this theta, this is also theta. So that we will get the distance up to z1, okay, then plus t1. So will be your x distance. So x equal to b plus t cos of plus t plus t1 cos theta plus t1. So that will be from point of intersection to the tangent point 3. We got it. then of course overall length equal to x plus a. So these are the formulae, so we can use for finding out the overall length at final. Okay, so this is something you should understand. Okay, it's just trigonometry, or to little, if you are able to concentrate, you are able to understand. Okay, so these are the equations we have at final, and these equations will be able to get the overall dimension, overall length at final. Okay, once you know the overall length, we can once the SRG is known, from here you can mark the distance equal to overall length, and perpendicular distance will determine your TP3. Okay, that's what. And as far as this point is concerned, you can work out TP2 distance also you can work out. Okay, the distance x is equal to this is one triangle, this one triangle. That means b plus t. Here now b plus t cos of, then plus t cos theta. Okay, t cos theta. You will be able to get this this distance. Okay, you can mark this TP2, and from here we can change the direction of the curve. This is the way to do it. Okay. So one more thing I want to say, in case of the reverse curve with the different radii and straight behind the hill. So in this case, how to modify this form? Only slight modification we do. So whatever thing we have discussed, the same thing only. Suppose we want to add straight behind the hill of crossing, so yes, distance we are adding. So wherever we have the b, that b we replace with the b plus s. That's all. Here you see, we have the formula b plus t. You simply put b plus s plus t. That's all. Okay. So that we have to add everywhere. And also here, see this theta also. Theta also we are adding wherever we have the r cos, then b sin of. So b plus s sin of. So wherever we have the b, you add simply s, b plus s. So we will get it. So suppose we want to have the different radius. Suppose here we want to have the radius of 1 or slightly here we want to increase more, or this thing. So this will become this we can keep as this is R2, here R1. So wherever we have the R, this triangle when we are solving, so there you put R2. So wherever this triangle comes, we put R1. Here you see R1. So here you put R2. Here in place of R we put R1. And 2R means R1 plus R2. So we mean R2 plus R1, like that. Only slight modification. So this is basic, this is trigonometrically we have made this equation. And according to the changes we want to apply, then slightly we modify the equation and we'll have it. So in case of only straight we want to add, only in place of b you add, you put a b plus s. Suppose you want to have different radius, and wherever we have the radius part comes, and you slightly make it R2 or R1, like that. Okay, slight modification we can do. Okay, this is something about it. Okay. Then we will go to the example. Okay, design example. So in this case, see broad gauge track. Okay, to be connected with this siding. We use 150 kg 1 in 8 of points on crossing, and curve also connecting curve we are using 1 in 8.5 turnout. And here there is no straight in between the reverse. Okay. Calculate the required distance or later they are asking. So the given is crossing angle, we know the distance they are given is 15 meter, and A and B the distance, of course we know this we can take from the table the standard measurement, and radius is 221.522, that is equal to the radius of the 1 in 8.5. They given radius solid curve minus j by 2. Okay, minus j by 2. This they given 221.522. So as usual, main thing we have to find out we want this x distance first. Then only we can find out overall length. Adding x plus a will get the overall length. So here yes, straight they are not given. So straight we can keep 0. So only we did not put B plus S, simply we can put B, that's all. So in between also, reverse curve also, there is no straight, 0 only. So same radius curve we are adopting. The distance they given 15 meter, that's all. So finding out the horizontal distance, up to this point, we want to get the up to this point. That we know B, S is 0, B and T we have to find out. For finding out the T, we must know the deflection angle. So deflection angle, for that, the theta we must know. That is why we are using this relation cos theta. So from here, so the relation we are able to get the theta. Once we know the deflection angle, the deflection angle minus F, this already we have discussed, we are at. This is theta minus F by 2. So theta we have found out now. F, the crossing angle. So using this relation T equal to R tan theta minus F by 2, we are able to find out the tangent length, that is coming around 15.193 meter. So we got the T. So once we know the T here, we can calculate the distance up to this. Okay. So similarly, we have to find out the distance up from here to this distance we have to find out. And what we do here, we know T, because since the angle of deflection angle is different, this tangent length also will differ. So you have to find out that this tangent length, this angle equal to actually theta, because earlier derivation we have got, no, this is actually theta. So from using this deflection angle, we can find out the tangent length 1 and using this R, same radius only we are using here. So T1 equal to R tan theta by 2. So this tangent length equal to T1 equal to 28.692. Okay, so with this we can find out the x distance up to this from a point of intersection to the this tangent point 2 we can find out. So first case, up to this B plus T cos F. Then from here T plus T1 cos theta plus T1. So substituting this value, we are able to get the x distance equal to 105.937. So x distance 105.937. To get the overall length, we are adding this A distance, A they are given 12.025 with the overall length. Okay, we get the overall length equal to 127.962 meter. So once we know the location of these points on crossing, the SRJ, we keep the overall length equal to 127.962. Sorry, I think there is some mistake is there. Here our x distance is 105.937 plus A is 12.025. So it will come only 117.962. Okay. So please correct it as this is 117. Okay. This is 117. Okay. That will determine the tangent point. Okay, up to this point the track will be parallel, and we can give the connection in between this heel of crossing and the tangent point 2. Okay, suppose you want to know the distance, this common tangent also you can find out. So that's this horizontal distance plus this horizontal distance. Here B plus T cos F, we can come up to this point, and this distance equal to, simply instead of put T plus T1, you can put T cos theta. So we can find out the horizontal distance up to the point. This is a common tangent point we can locate. Okay, so we can introduce curve from wheel of crossing to this point, and again reverse curve from this common tangent to the tangent point to this way. Okay, this is the way how to do it. Suppose in case you want to have the S straight after the heel of crossing, wherever we have the B, you add B plus S. Okay, B plus S you put, so that sub 6 meter after heel of crossing we want to have the straight plus B plus S. Okay, we can do it like this. Okay? This is a way we are designing location. Okay, as far as this connection is concerned. Okay, we'll go to the next. This is connection to straight parallel tracks with the reverse curves and straight. Okay, So earlier case there was no straight in between. Now we want to give straight in between because the distance is somewhat larger, some 50 meters, 60 meters. We want to introduce some straight in between. Okay. This is the detailed drawing of this connection. It's like a previous example only. The only difference is we have the straight in between the reverse curve. That's all. So one S is coming into play here. All the things are same, and because of that, so the one psi angle is involved. That means as usual, we have to solve this trigonometrically. So we have to conveniently make some triangles, okay, and we have to find out the required dimensions. For first, we have to mainly we want to know our x distance. For x distance, we want to know horizontal distances. That means we are conveniently making many triangles, and we are adding all horizontal distances. We will be able to get the x. So first triangle this one, and second triangle this one, and third one. Straight away we can add with the T2, okay, the tangent length of this curve. So we will be able to get the x distance. And further, here the problem is the tangent length we have to find out. This tangent length and this tangent length. This B, of course, we know it is standard measurement, okay. Then S also we know that we are only deciding it. But T2 we have to find out. Deflection angle we must get for this also. So for finding out the deflection angle, this deflection angle we have to find out. That means this included angle we must know. That means angle subtended the center of this arc, we must know. So once we know, that will be equal to your deflection angle. So that is why, like previous case, we are making a so triangle to resolve this this angle, total angle. So now we are connecting the centers of the two curves, and we are assuming here taking radius of curve is equal, and both connecting curve radius is equal. Okay, this is your D. Okay, so once we are connecting it, so the total angle will be equal to this. We are keeping as here some angle. This is one angle, and another angle is this one. Okay, the total angle will be, suppose this is theta plus psi will be total angle. Okay, so once we resolve this triangle, that means the cos of this angle equal to, what is this, adjacent side O1 N1 divided by this O1 O2 will be your cos theta plus psi. Okay, and from there we have to find out the theta. Once we know the theta, whatever angle we calculate now, this minus this will give you the deflection angle. This is a procedure like previous case we have to do it. That the earlier case, the O1 O2 when we are connected was passing through the common tangent point. Okay, but here also we have common tangent, but there is no common tangent point. Okay, that is why when we are connecting the O1 O2, it will give for some slight inclination. Okay, that angle equal to psi. It was passing through center of the straight. Actually, the line is passing center of the straight. Okay, then how to resolve this? Suppose let us take this triangle. Okay, and before that, first let us know what is psi angle. So tan psi, let us take this triangle O1, TP2, and this Z. Okay, Z3. From there we take it as tan psi equal to this one, S by 2. Center of curve, center of straight only passing through. No, it is S by 2 divided by R. So psi equal to tan inverse of S by 2R. So we form one equation. Then again, as usual, we come to this big triangle O1, N, and O2. So cos theta psi equal to what? This adjacent side O1 N and divided by O1 O2. So we are resolving it. Again, we resolve that O1 O2. It is not 2R. Simply we cannot take it, but we are taking in terms of psi. So in terms of psi, if you want to know, O1 O2 equal to S by sin A. S by sin psi. So then we are substituting a cos theta plus psi equal to this. Okay, that means adjacent side angle divided by hypotenuse. So from there we are resolving for theta. So So we are able to get the theta angle. And after the theta, we are substituting, once we know theta, this angle is f. Already previous example also we have solved, theta. This is, sorry, and previous example also we have solved this angle is f only, because this triangle, this is f means this is f, this is 90 minus f, and total 180 minus 90 minus f minus 90, it's f will get, okay. So like that. So this will be equal to theta minus f. The deflection angle equal to theta minus f. When theta minus f will be your theta. This is deflection angle. So knowing all deflection angle, we are able to get tangent length. And finally, we find out the horizontal distance. First, we take this triangle b plus t1 cos f, and second triangle, this triangle t1 plus s plus t2 cos theta. Up to this we are coming. Then plus t2 will be your total distance of x. Once you know the x, you can find out the overall length, that is equal to x plus a. That's all. This is about this connection, and also this is general form of equation, and we can suitably alter according to the need. Suppose you want to introduce the straight after the heel, in place of b you substitute b plus f. Suppose you want to have different AD, in place of or, this or, wherever it comes, you put different r1 or something you put and change it. That's all. Substitute it, you will be able to get this type of equation. Okay, this is something about just to spare some few minutes. If you deeply involve and understand, you will be able to get things. Okay, this is very simple. Okay, then coming to the example here, the same example, previous example, example 4, that we have taken. In that now the 10 meter straight is added. So how to add? So as usual, we simply have to substitute in the equation. We have psi value we have to find out. Yes, we know 10 meter, and r also we use only same 1 unit of turn out radius. That means 221 something, 522. That we are, so resolving it, we are getting our psi value. And another for finding out the cos theta. Okay, and we are using this equation, and finally we are finding out theta using this relation. We are getting 13 degree 18 something, and after tangent length, this we have to find out r tan theta divided by 2, 12 point. First the tangent we are getting 12.78, and tangent 2, this, let us take this tangent 2, that we got 25.862, and we want to find out the x. We come up to this point. Okay, now yes, here s is there, here s is 0 now, because we don't have any straight after the heel occurring as with this problem is concerned. So here b plus t cos of, then t, this s plus t2 here. So we are able to get total this distance. Okay, so we are able to get the distance up to this point. Then again we are adding the t2, this distance we are adding, so that we are able to get the x distance. Okay, so first we are coming up to this point, and second triangle we are from here to this point, we are finding out this horizontal distance. Then third we are calculating this distance. Adding all, we are able to get x, and x plus a will give you overall length. So overall length now is coming this 117.608. Okay, so this x distance is 105.583, adding 12.025, we are getting 117.608. Okay, so this is something about the calculation of the required dimensions for fixing the geometry. So once we know the x overall length from SRJ, after locating the SRJ, we fix the point here, and perpendicular distance will, perpendicular line will make the TP2, okay, location. So we will do the connection. Only thing we want to introduce this point, we want to know this connect point, simply you can use it. S is 0, let us take. So b plus t cos f plus t cos theta will be the distance, horizontal distance. Okay. Again, S distance can straight, or you can, we want to S1. Okay, here S1 cos theta, horizontal this distance, and again this one T1 cos theta this distance. Then T1 or T2, whatever. If you are assigning T2, you put T2. We are assigning T1 means T1. Okay, T1. That's all. This is a way you have to only just a little application of mind will be able to resolve this trigonometrically. Okay, this is nothing about it. Okay. So we have seen so far, the divergent track connections, and as well as the connection to the parallel tracks, how they have to be designed, and all we have seen. And with that, we will conclude this video, and the remaining part, regarding crossover connection and all, we'll see in the next video, along with the web applications. I have my website, V.Thiagarajan.com. There we have the layout connections, designs and all available. So that also we'll see some one or two example. We'll see. Okay. Thank you. Thanks a lot.